The components of piston engines are subjected to high loads, high temperatures, and high speeds. As the components slide against each other, a force is generated which resists their movement. This force is called friction. The friction produced will increase as the load on the components, their temperature, and the speed at which they are rubbing together increases. The fact that the components rub together also produces wear, which is evinced by the partial loss or destruction of the metal components. Both friction and wear can be reduced by preventing the moving surfaces coming into contact, by separating them with a substance which has lower frictional properties than the component parts. This substance is referred to as a lubricant. Lubricants come in many forms. Grease, powder, and even air can be used as a lubricating substance. However, this lesson will concentrate on the use of oil as a lubricant. There are 4 methods of lubricating the moving parts of an engine with oil. They are the petroil system, where lubricating oil is mixed with the fuel. This system is used mostly in small 2-stroke engines. The pressure system, which has a high-pressure oil pump incorporated in the design, which supplies oil under pressure for lubrication of the major components. The splash system, where oil is thrown onto the major components by the rotation of the crankshaft in the oil sump. And the combination pressure splash method, whereby the major components are supplied by pressure oil from a pump, and remaining components are supplied by splash lubrication. Most modern generation engines use the combination pressure splash method. However, there are 2 types of systems available for controlling and delivering the oil to the engine components. They are the wet sump system and the dry sump system. The primary task of the lubrication system of the engine is to reduce friction and component wear. It also has a number of secondary functions. Of these secondary functions of the lubrication system, perhaps the most important is the task of cooling. The flow of oil through the engine helps to remove the heat from the internal components of the engine. This heat can then be dissipated in a radiator, which must be exposed to the cooling effect of the air flowing past or through the engine cowlings. As the oil flows through the engine, it also carries away unwanted foreign particles, and also the byproducts of the combustion process, such as carbon, which forms on the piston crown, varnish, which forms on the piston skirts, and grease-like sludge in the crankcase. These deposits are strained out of the oil by the oil filter. Thus the oil can be said to clean the engine. The internal metal components are protected against corrosion by the lubricant, particularly if it contains a proportion of fatty oil, a thin film of which tends to stick to the metal surfaces. The oil can act as a hydraulic medium in 2 ways. Firstly, it can provide the power source for the operation of various components on the engine, such as variable pitch propellers. Secondly, it also acts as a hydraulic medium by reducing the shock loading between the shafts and bearings in the engine, thus reducing vibration. The oil system's use as an indicating medium is of great importance to the pilot, as it can give an early warning of impending mechanical failure or loss of power. The lubricant can be used to show the condition of the engine, both in terms of its oil temperature and its oil pressure. On some engines, the oil can also be used in a torque meter to show the power being developed. It should be remembered that an increase in friction will cause an increase in friction horsepower, and therefore a reduction in the brake horsepower developed by the engine. Thus, the ability of the lubricant to reduce friction and wear is of prime importance, but the secondary functions of the lubricant, such as cooling, cleaning, corrosion protection, and as hydraulic and indicating mediums, should not be ignored. There are 2 lubrication systems in common use in aircraft engines. They are the wet sump and dry sump systems. The system used is normally dependent on the power output of the engine and the role of the aircraft. The principle of lubrication of the engine is the same whichever system is used. The main difference between the two systems being the method which is used to store the supply of oil. Most light, non-aerobatic aircraft engines use the wet sump system. In this system, the oil is stored in the bottom or sump of the engine. This method simplifies the construction of the engine, but it has a number of disadvantages. The first of these disadvantages is that lubrication difficulties arise during aircraft maneuvers. The oil enters the crankcase, is flung around by the revolving shafts, possibly causing both over- and under-oiling of the engine, inverted flight being a particularly hazardous undertaking for the wet sump engine. Of the heat energy available in the fuel, up to 25% is wasted as cooling losses. Of this, up to 10% is removed from the engine by lubricating oil. As it's stored within the hot engine casing, the temperature of the oil is difficult to control. The oil becomes contaminated and oxidizes more easily because of the continual contact of the oil with the hot engine. For instance, a plain hydrocarbon oil, under the conditions of high temperature which it will endure inside the sump, will start to crack or break down, and also combine with some of the free oxygen remaining from the combustion products. Finally, the oil supply is limited by the sump capacity. The dry sump system overcomes these problems by storing the oil in a remotely mounted tank. As previously stated, the principle of oil supply is the same for both wet and dry sump systems. Both use the combination method of pressure and splash lubrication, after which the oil is returned to the engine sump by gravity. In a dry sump system, however, one or more scavenge pumps return the oil from the sump to the tank, to prevent flooding of the engine sump. The arrangement of the oil systems in different aircraft engines varies widely. However, the functions of all such systems are the same. A study of one system will clarify the general operation and maintenance requirements of other systems. The principal units in a typical reciprocating engine oil system includes oil filters, pressure and scavenge pumps, oil cooler, oil pressure and temperature gauges, plus the necessary interconnecting oil lines, and, in the dry sump engine, an oil tank. All of these components are shown here. This diagram illustrates a dry sump system. Remember, the oil tank would not be necessary in a wet sump system. Oil tanks are made of sheet metal, suitably baffled and strengthened internally to prevent damage due to the oil surging during aircraft maneuvers. The tank is placed, whenever possible, at a higher level than the engine to enable a gravity feed to the pressure pump. The tank forms a reservoir of oil, large enough for the engine's requirements, plus an airspace. The airspace is necessary to cater for several situations. For instance, the increased oil return when starting the engine. When, after a run, the engine is stopped, the walls of the crankcase are saturated with oil, which will drain into the sump. The oil will remain there until the engine is started, when the scavenge pump will return it to the tank. Next, the expansion of the oil, and therefore its greater volume as the oil absorbs heat from the bearings, necessitates a greater volume of space than otherwise would be the case if the oil was cold. Likewise, the oil suffers quite a beating from the engine components, as they attempt to thrash air into it in a similar manner to the preparation of a soufflé. This aeration causes the oil to froth, which greatly increases its volume. Another reason why the airspace is necessary is the fact that oil can be displaced from the variable pitch propeller and any other automatic controlling devices when they're used. The hot pot forms a separate compartment within the oil tank. Its purpose is to reduce the time taken to raise the temperature of the oil when starting the engine from cold, by restricting the quantity of oil in circulation when the oil is cold and viscous. The hot pot consists of a cylinder of metal fitted above the oil outlet to the engine. The oil must pass through the hot pot to reach the pressure pump. During engine start, the level of oil in the hot pot drops as it's taken into the engine. This uncovers a ring of small diameter ports which are cut in the wall of the hot pot. These ports offer a high resistance to the flow of cold, thick oil, so that very little of it passes into the hot pot to join the oil going into the pressure pump. Nevertheless, it is this oil, and the oil which was already in the hot pot, which is passed to the engine and then recirculated. After passing through the engine, the now hot oil is returned to the tank, where its heat raises the temperature of the walls of the hot pot. The oil in the immediate vicinity outside of the walls of the hot pot is also heated, and becomes less viscous as a consequence, so that the ports offer less resistance to its flow, and progressively more and more oil is brought into circulation. If a feathering propeller is fitted to the engine, the lower ring of feed ports in the hot pot are placed above the bottom of the tank. This provides a feathering reserve of oil, even if the main tank has been emptied through the normal outlet, as may occur if the main feed pipeline was to develop a leak or completely fail. Scavenge oil from the engine sump is passed over a de-aerator plate to the inside of the hot pot. The plate separates the air from the oil to reduce frothing. The oil tank is vented through the crankcase breather to prevent oil losses during excessive frothing conditions.